So, good afternoon, everyone, and welcome to the second midterm webinar of Code for Earth 2024. My name is Satina, and I'm here with my colleague Esperanza Quatero and with Sara Bozzi from our supporting company. And before I start, I would like to hand over to Sara for some logistics. Sara, please.
Yes. So, hi everyone. Pleasure to have you here. Just a quick PSA. So, whenever you have a question and after the presentation, we invite you to please wait until the end of the presentation to write your message, to write your questions, and we will answer all of your questions right after each presentation. We will also probably have like a short Q&A session at the end for any general question you might have. And for anything else, feel free to write, please, in the chat. But for the questions, please write in the Q&A section of Zoom. You can find it at the bottom. And thank you, everyone, and enjoy the webinar.
Okay, perfect. Thanks, Sara. So I'm here, as I mentioned, with my colleague Esperanza, and most importantly, the participants of 7 of the 13 selected projects of Code for Earth in 2024. Let me do a quick summary, quick facts on Code for Earth. Most of you probably know that this program, Code for Earth, is a key innovation activity run by the ECMWF and supported by Copernicus and Destination Earth. We welcome each summer individuals and developer teams with a different background. That can be, in earth science. It could be also computer science, software development. The variety is really broad. And the program puts up real-world scenarios, problem statements, and the main focus is really on innovation, collaboration, and open source software development. Those selected teams that finish with the coding phase that goes from May to August, that successfully finish the coding phase, they receive a 5,000 euro stipend. So we have been, here a short infographic or a timeline of the project of Code for Earth in 2024. So we started the call for participation end of February. After we received all the proposals, and we received a lot of proposals, we evaluated them, and then end of April, we announced the selected proposals. And in May, we started the coding phase. Well, that goes until 31st of August. On today, we want to share, or the teams, we want to give the teams the opportunity to show what they have been doing so far. So this is where we are at the moment. I would like to highlight 2 of our supporters, especially, that's Helmholtz-Zentrum Herion in Gestacht, northern Germany. They are jointly with the ECMWF colleagues, they have set up a challenge, and they are mentoring one of the projects. And I want also to highlight a contribution from IFAB, the International Foundation on Big Data and Artificial Intelligence for Human Development. So I would like to hand now over to Esperanza.
Thank you, Tina. Thank you, Tina. Code, as Tina says, Code for Earth is a mentorship and collaborative program. So mentors are a key part of our program. So not only came up with the original idea of the challenge, but now during this coding phase, mentors are putting their expertise, and they are helping the teams to working on the ongoing projects. So on the screen, you can see all the mentors in 2024, 40 names. We're very pleased to them to collaborate with us, and you can see all these names on the screen. Yes, last week, the first midterm webinar took place, and during this session, 6 selected teams presented their projects. If you miss this session, don't worry, because we record it, and all the recordings will be available the last week seminar, and today's seminar will be available on our YouTube channel and also on our website next week. And now, without any delay, this is time. We are very pleased to have with us on the spotlight the 7 remaining teams who are presenting now their progress and introduce their open source developments so far. So I'm going to start with the first team. Is the project's name's AirQuality Urban View. We have the pleasure to listen to Eloi, Codina, and Oscar Hernández. The floor is yours. When you are ready, please. I hand over you.
Thank you, Esperanza. I will share my screen for you to see the presentation. Okay, can you see it? Okay, so we are Andrei, Eloi, Codina, and Oscar Hernández, and we are the team.
Sorry, Oscar, you are showing the presenter view, not the
thank you. Okay. Okay.
We can now see it, yes.
Okay. We are Andrei, Eloi, Codina, and Oscar Hernández, and we are working in this project called Regional to Urban Air Quality Mapper, together with our mentors, Miha, Johannes, and Martin. So, which is the goal of the challenge that we are working in? So our challenge consists in downscaling ground level pollutant concentration data from a regional scale to a urban scale. That means that we have the CAMS reanalysis air quality data, which is a data set with a 10 kilometers resolution. And we want to get a urban resolution data set of pollutant concentrations, more or less 100 meters. So this is the challenge that we have to face. And the proposed approach, so the approach that we have proposed is to develop a machine learning model that takes this data from CAMS reanalysis and improves the data set by training together with other sources, topography, meteorology data, population, building height, roads, and so on, so as to achieve this urban scale. And then, so as to evaluate the machine learning model developed, we use the recommendations from Fairmont so as to validate them, to validate the output against ground-based measurements from the European Environment Agency. So these are the general steps that we are following during this project. First, we did a data integration of all the data sets that we are using for the machine learning model, including the interpolation and preprocessing of data. Then we have trained the model in different versions using different sets of data sets and different configurations. Then we have done the inference of the model. So we have applied that model to get an output, to get a urban resolution air quality data. And finally, the final step is to validate those output data from the different model versions so as to compare the different versions and also to compare them with other models. So the machine learning model specifications that we are using until now, maybe we will extend those specifications, but until now we have also focused, we have only focused in NO2 as a pollutant. So we are working with NO2 data. Our model is considering the year 2022. We wanted to discard the pandemic period. So we are working with this year. The time resolution is 1 hour. And we are focusing into the Iberian Peninsula urban areas. So to do that, we are working with the European Environment Agency stations in Iberia Peninsula. To train and also to validate the model, but we are not using all of them. We're just using those stations that are located in urban areas. And to select those stations, we applied a clustering to the stations so as to get only those stations which are located in high density areas with a high density of stations. And we can see here some clusters which corresponds to the main cities in Spain and Portugal, Madrid, Lisbon, Barcelona, and so on. Okay, so to train our machine learning model, what we have done is first we have selected one station from each cluster, and we have used that station for training purposes, for the validation for training purposes. Then we have interpolated all the data sets that we are using as inputs in our model into the locations of those selected stations. And finally, we have applied a regression machine learning algorithm. We have chosen a gradient boosting algorithm, but we could test other algorithms as well, which try to fit the data sets data so as to reproduce the values from the station. So the way that we have done the inference of the machine learning model is the following. First, the main data source that we are using is, as I have said, the CAMS reanalysis data, which is a data set of a 10 kilometers resolution. First, we needed to interpolate those data from 10 kilometers to 100 meters. We have done an interpolation. On the other hand, we have also the data from the EEA stations, which we have also interpolated within the urban areas clusters. And finally, we have all the other data sets, which are not mandatory. They are not all used in all the versions of the model. And those are the topography from NASA, the land use from Korean land coverage, the meteorology data from Era 5 reanalysis and Era 5 land reanalysis, and also population and building heights data from GHS. So those are the data sets that we are using to input into the model, and the outputs are the values for the year 2022 in an hourly resolution for the Iberian Peninsula. So as to try several configurations of the model, we have defined until now 8 versions of the model. We have a version without any extra data set, using only the CAMS reanalysis and the interpolated EEA stations data. And we have other experiments adding some of those additional data sets that can be fed into the model. So we have those 8 versions of the model. And once we have tried the model with all those versions, we need to evaluate the quality of the model. We need to validate the data, and to do that we have reference to the FAIRMOD recommendations. So FAIRMOD says that modeling quality indicators should be used. Here we can see the definition of this MQI, which is a ratio between the root mean square error of the model and root mean square of the uncertainty of the observational data based on reference values, which depend on the specific pollutant that we are trying to validate. So this is the definition of MQI, and it has also a proportionality factor, beta. So a correct model performance is reflected when MQI values are lower than 1. So these have been calculated for each station, but so as to check the global model quality, we have computed the MQI that corresponds to the 90th percentile of the stations. So this MQI 90th is the value which ensures that the 90% of stations have a lower MQI than this MQI 90th. So finally, here we have the results of the experiments and the MQI 90th values. As we can see, the better performance, as we could see, is those from the latest experiments, which considers a bigger amount of data sets. And the worst experiment, the worst model version is that one that only use the mandatory data. We will keep working on those results. So the next steps are maybe to study the inclusion of raw data into the model, because we think that this could make a big change into the model. Also, we are working into plotting some target diagrams so as to study the model's behavior within certain urban areas. We are also studying to extend the time period that we are working with to other years besides 2022. And also we want to compare our model with this CAMS European air quality forecast optimized as at observation site, which also has a high resolution and could be a good reference to check whether our machine learning model is improving those data. And finally, we will also work into extend the model to other urban regions in Europe. Okay, thank you very much.
Thank you very much, Oscar, and Eloi and Andrea, who are the members of this team. So very well done. So I don't know, we were questions relating to this project, Air Quality Urban View. It seems, there's one. It's yes. Why, it's to Oscar, why did you use SRTM and the better and more current data sets available? COP10 or locally city models?
So as we are talking about topography, so topography is a static data set. So we thought at the beginning of the project that it wouldn't make a big difference which specific data set we're using to get the elevation data from, but we could study other sources.
Thank you. Thank you. There's there's another one, or no? This is the only one. So we can pass now on to the second project. It's invited. It was here with us. Is CAMS Verisualiser, and it is formed by 3 members: Hakan, Deniz, Kale, Yavuk, Arda, Urak, and Elif, Rana, Arslan. But the speaker today is Hakan. The floor is yours. Hakan, when you are ready, you can start introducing your project. Thank you.
Thank you. Can everyone see this?
Yes.
Yes.
So, hi, I'm Hakan. I'll be presenting on our project CAMS Verisualiser. At the end of his presentation, Oscar talked a bit about that they would compare their data with the CAMS forecasts. Our project CAMS Verisualiser is actually very much about this, as our application is made to compare the actual observation data with the forecasts. So that's basically what that is. The current software used at the ECMWF generates a lot of static plots, which take a lot of space and are also not used a lot. So our project basically aims to make this dynamic and directly generate the plots from the data on user request. We had a lot of challenges, of course, when doing this project, and like specific to our challenge was that our application needed to be very fast in getting the data and getting a plot to the user, as of course, when a user wants to see something, they should see it nearly immediately. And other than that, we would have a lot of the data we need to take from to make the plots from does need to be, this is also a kind of a challenge of our mentors as well, I guess, needs to be standardized a bit before we use it, such that it's easy to compare. So that was a challenge we had. And we also wanted this application to be used maybe even years into the future. So that's also something we try to take into account when developing. A kind of a specific to our team was that we are quite inexperienced, and as we are, we have like 3 team members, and we have all just graduated from high school. So that was also a great challenge we had while developing. I want to talk very shortly on how we implemented this, how we want to implement this. So basically, the data is, let's say, it's stored in a file system. Our web application would first, so we would have an API for handling all data and have a web application for showing it. And firstly, our web application would take like all the available data, like get what is available in order to construct a front end for the user. And once it's constructed, the front end would communicate with our API to get make further requests on what is available based on what the user has selected on the front end. And at the end, of course, the user would make a request to plot the data and get the plotting data, which would then be plotted on the front end. So what we found important in this part was to separate the front end and back end, such that even if we use a web application right now, if for example, if someone wanted to use a script in another language or like make another front end in another language, this would allow that. And we also need to change how the data is stored, as it was like all of the plots were stored statically somewhere before, and now we are storing the data directly. And we would need to, like for understanding the application better, as well as working with it better and doing things easier, we would need to store data according to its usage. That was also something we took into account. Now I would like to shortly show you what we have currently. It's quite like the old application used. On the right, you select some things, and on the left, you get a plot, or maybe more plots in the future. This is very bare bones for now, but we just want to show what we had in mind while developing this. And yes, that was our presentation. Thanks for listening.
Thank you very much, Hakan. Thank you. Very nice insights. We're very, very good. Well done. So if there's questions from Kahan, please, you can type in the Q&A. And Hakan is willing to answer it. So it doesn't seem that there will have any question.
But sorry, Esperanza.
Yes.
We can still have, questions later also for Hakan. So we have a Q&A session. So
yes, exactly. At the end of the presentations, yes, we open this turn for Q&A. Exactly. So we are now advanced. We are with the 3 team, which project is HydroGap-AI, and it is formed for Yiannis, Kontos, Constance, Plataridis, Diamantis, Karaxanis, Ries, Stavridis, Nikos Cepho, and Constance Perifanous. So the presenters now is Yiannis and Kostas. Please, the floor is yours. You can start now.
Let me just share my screen. I hope you can see it in full screen mode.
Not yet. No, perfect.
Okay. So we're talking about the HydroGap-AI project, which is part of Challenge 20, bridging gaps in streamflow observations with machine learning-driven solutions. Number 2, I will be speaking on behalf of my team. The members, you already tried to made a really good effort to pronounce them.
Sorry about that.
It's all Greek to you, I know. The main goals of this project is to investigate methods for gap filling daily streamflow time series, evaluate effectiveness and identify the longest reliable gap fill, develop a Python-based open source software package, and it is necessary to address limitations in forecasting due to data scarcity and quality. This is the case in many GO stations, at least in Greece, which has problematic stations and really few stations, at least in our country. And we also want to ensure continuous time series for better prediction and evaluation. So basically, filling the gaps will also help other machine learning projects that want to use streamflow time series as their input data. So their accuracy will depend on our accuracy of prediction and gap filling. So the objectives of the project will be to produce navigable, well-documented Python code, offer multiple alternatives for gap filling. This is something that we really want to focus on, just not just provide one method, but many alternate ones, so that the user can use the one that is more accurate for his or her input data. Also want to provide technical performance details, the maximum reliable gap size, degradation table, etc. The benefits will be to assist users in choosing optimal gap filling methods, foster community collaboration, and integrate machine learning, hydrology, and software development skills. This is something essential for hydrology. I don't know about the structure of the other teams, but in our case, we're more, let's say, relevant to hydrology ourselves than the machine learning, IT science. So it is something that we really need. We want to address our own problems in scarce data in stream flows. So it is essential for water management, disaster mitigation, like flood protection and flood mitigation, hydraulic design. So complete stream flow time series are critical for decision makers. The challenges are that missing data are common due to errors, equipment failure, or weather events. We currently saw a GOES station in the Thessaly region in Greece that actually recorded its own demise, its own destruction. When the Daniel Medicane reached the height of 2 meters, the station just ceased to work. So we've seen it in with our own eyes. So, and of course, one challenge is that linear relationships at high complexity in streamflow prediction make this problem even more complex. In literature, as far as direct future streamflow prediction is concerned, because there's not much literature in gap filling per se. So the most popular in literature machine learning models are artificial neural networks, the classic ones, support vector machines. These have some limitations due to lack of transparency in output estimates. And the more advanced machine learning models are the random forest, multiple linear regression, convolutional neural networks, mixed forest, which is a variation of random forest, just adjusted to gap filling, Gaussian processes and decision trees. The challenge in these models is, of course, as in any model, deep learning model, the hyperparameter tuning, which is demanding and time consuming. So the applied algorithms that we found in our preliminary in the writing of proposal, actually, literature review, were gray wolf optimization, particle swarm, genetic algorithms, and some more, as you see. The superior performance was in the hybrid models, especially with Harris-Hock optimizer. Of course, these generalized conclusions, when someone reads the literature, are not accurate necessarily, as we do not know, of course, if the users actually did the best parameterization of the models. So the preliminary state-of-the-art investigation, we have done that. We will show it in the next table. We have some key information regarding the various machine learning methods used for streamflow data gap filling, references to respective scientific papers, machine learning models used, the optimization methods optionally used for hyperparameter estimation, and the respective evaluation metrics, input data types, and time steps used. This we needed in order to select the best models, hyperparameter optimization methods, and metrics for our case, for all the models that we want to implement. So to the best of our knowledge, the state-of-the-art pinpoints that there is a gap regarding the existence of respective open source Python libraries for streamflow, gap filling. And many machine learning methods have not been used for the current problem, the gap filling of streamflows. So under HydroGap-AI project, anyone interested can ask for this detailed, which is updated now, review in literature concerning the models and other methods used for gap filling. So the motivation is the missing data in time series for monitoring station errors are there. We see it in our own Go stations. There is loss of the valuable data for hydraulic calculations and regime understanding, flow regime, I mean. The team expertise is actually is based on daily use of hydrological and streamflow data. Since we implement the digital twins, we design and operate digital twins in some horizon projects that we have. The current one is in Aliakmanas water basin, river basin in northern Greece. We have our own DIY gauge meters, and we also use the formal state ones, let's say. So we have a focus on hydrology, hydraulics, water source management, and land use interactions with all of these. And we actually have an expertise in application in designing hydraulic works, even small dams, system of dams, flood mitigation, including nature-based solutions. So we have a diverse set of researchers in our team. So there is only a 4-month implementation timetable, of course, so we focus on efficient, credible, and applicable methods. So we want to test various methods for gap filling streamflow time series, evaluate the time series extension and temporal disaggregation as a secondary goal. We will focus on head catchments, but we want, if we have the time, to also address complex cases of nested, linked head catchment and sub-catchments. So we would like to have the opportunity, even after the completion of the last deadline, to address this issue not only as ML users in a black box situation, but as hydrologists knowing the interactions of precipitation and stream flows. So the methods that we are implementing is the support vector machine linear regression. Okay, this is just a reference. The method, the KNN naive Bayes Miss Forest, which is a variation of random forest, XGBoost Light GBM, GPR, the classic artificial neural networks, the long-term memory neural networks, and the computer vision one, CNN. So we have found out that we need to have some pre-processing techniques, perhaps different in its method, but we have to normalize and adjust data to a common scale, ensure fair interpretation by models, prevent bias from features on larger scales, and of course, some additional pre-processing. We have to standardize min-max scale, robust scale, and among others. The most crucial thing in time series prediction and gap filling is the lag time identification, which is essential for accurate prediction, and it captures dependencies across time. We ourselves understand the physical actually lag time, not only from the stream flow data as input data to the output stream flow data, but also to the precipitation to stream flow conversion, let's say, which is actually which could actually, in its case study, in its GOES station, be analyzed hydrologically. This would, of course, better our understanding of the problem, and it would make us select the lag time from precipitation as input to stream flow as output in a better way, in a more realistic way. We hope that we will have the time to do at least some ideal, let's say, GOES stations and implement this more, let's say, advanced method, hydrological, let's say, wise advanced. So the methods will be to find out the lag time apart from this, let's say, realistic one, which will need hydrological and hydraulic numerical models implemented. So the standard methods are trial and error, autocorrelation, and partial autocorrelation. The metrics that we're going to use, we can see them, it's quite standard, and we have to, of course, provide documentation for the user to be able to understand which method will be used and why. Of course, the final goal is to create free Python libraries for broader user access. We will use some hardware, Google Colab, and of course, our team of mentors have set up a virtual machine for us, which is really good for the really demanding CPU demanding and graphics demanding machine learning methods. And of course, we will use Python. This is our timetable. Of course, we have rescheduled it a bit. And our milestones, anyone can see this. So this is the kind of data that we were provided with. It's actually a really big data set from the whole world, from 1970s, roughly up to 2015. And we can see there are many, apart from the location data. So this is stations per country figure. Of course, most of them are in the United States and Canada and Brazil. Europe and other countries is not really rich in these GOES stations. So we can see the first station that is in the dataset, and the actual data that we tried to, we filtered, we used these ones together with, of course, the day, month, and year, which can be extracted from time. So we can see TP, which is actually the total precipitation, so which is actually the cause in this phenomenon of the stream flow, and this is the observed discharge, the stream flow in cubic meters per day, and total precipitation in meters per day. We can see in Europe the distribution of stations, USA, Africa, Asia, Australia. We have consumed a lot of time for the processing of data, because not all datasets are the same. We have approximately 1,450 datasets. Some of them have a lot of gaps. most of them end at 2015. So you can see all the variation. So let me just show you, because we don't have much time, one of our current work results. Of course, it is a work in progress. So we can see station 916. I will provide info on why we used that one, and I decided to present this one. So it's a Yangtze River GO station in China. I will show you a random forest example. So in this example, we standardize features at first. Input data are precipitation and stream flow itself. So we removed the mean and scaling to unit variance. We had autocorrelation, cross-correlation. Autocorrelation meaning just for the stream flow as input, and cross-correlation, precipitation versus stream flow correlation. So at this point, of course, we will automate that. We visually define the lag times of stream flow and precipitation. We created a daytime features due to the seasonality of the time series to serve as input. So month, year, quarter of the year. If we had hourly data, we should perhaps take the day. And we created the dummy variables binary of these features just to help the algorithms, the methods. We defined the number of days for forecasting, which is variable in our test cases. We split the data into training and testing sets, fit a random forest model in the training set. We made predictions using a recursive multi-step forecasting approach. We had direct implementation also, but I will present just this today. So we did predictions that are used as input for the next day. And we denormalized the predicted values and plot them via the actual values and calculated various metrics. So this is the example of the results we had. We used lag times after this visual inspection of the trilander, of the autocorrelation, partial correlation results. So the concerning the stream flows, we had 1, 2, 3, -1, 2, 3, and 4. Sorry for that. 1, 2, and 3 for stream flows, and 1 to 6 for precipitation. So you can see the metrics of the random forest for these days ahead. 7, 14, 21, 30, 60, 180, and a whole year. So these are...
Sorry, Yiannis.
I should conclude.
Sorry.
Yeah, sorry.
Thank you.
I got carried away. So we can see the visualization of the various gaps and gap lengths. This is a whole year. Actual values black, predicted values red. So anyway, I want to conclude with that. We have a really good pre-processing section that we actually produce a lot of gap and values, input and output characteristics, so that for each station, these will characterize the stations. So once we have, we follow a specific workflow from a really renowned paper for gap filling that uses mist forest, the variation of random forest. So what we're going to do is to use these artificial gaps in the solid, in the best time series that are not altered by human, let's say, hands, dams, diversions, because these are actually more correlated precipitation to stream flow. The other ones are really, really more complex, and we will try to use these ones, some of the best correlated precipitation to stream flow ones, as our basis with artificial gaps, and then go to the real time series. And then each time series will have its own result in the metrics for each method. And with a machine learning algorithm, the user can provide his or her own time series, and it will be characterized by the machine learning so as for the user to understand which of these methods should have the best results. Sorry for the time.
Okay, thank you, Yiannis, for a good presentation. I think there is no posted questions for you, but there will be an opportunity at the end of the presentations.
Of course.
If someone has raised a question to you. addressed to you. So the next project with us is Project Poly. Is formed by 3 team members: Clive, Drowley, Kaitlyn, Ries, and Nadia, Skifa. So the floor is yours. The 3 of them are united to speak about the project. Please introduce. The floor is yours.
Thank you. I'll just share my screen. There we go. I believe you could see my screen, right?
Yes, yes.
Perfect. Okay. We are Project Poly, and our project looked at using a natural language processing interface to extract complex features from weather data cubes. So this is us. We are all doing a CDT in geospatial engineering at Newcastle Uni. You can see our names and the title of our projects. So our main objective is to develop a machine learning chatbot user interface to retrieve user-specified queries from the ECMWF using Polytope. And if we get time, our secondary goal would be to design a web interface for this chatbot. So what is the main motivation behind this project? So here we have a simple user chatbot conversation where the user asks the chatbot to retrieve the temperature for London yesterday at 10 a.m., for example, and the chatbot comes back with a COV JSON that's too complicated, not easy to understand for a user. So how can we allow our users to retrieve large amounts of data depending on their input features, whether it was countries, cities, time series, or more complicated spatiotemporal paths, such as flight paths, or maybe shapefiles or geo packages. So what is MARS? MARS stands for the Meteorological Archival and Retrieval System. It is the data management system designed by the ECMWF to store and retrieve meteorological data. This system supports a wide range of data that optimizes high-performance data access. But how do users only retrieve the data that they want? So each data set within the MARS is composed of multiple data cubes. However, the user doesn't want the whole data cube for that specific feature. Then Polytope allows to handle complex queries and massive datasets efficiently to only extract the data in regards to the shape or feature that the user wants. Now moving on to large language models. So a large language model is a type of NLP. We use it to answer questions with human-like responses. We also use RAG. RAG is a retrieval augmented generation. It can be used to improve the accuracy and reliability of AI. So, for example, we gave it all the documentation on Mars so that it can quote things straight from the document.
Perfect. And then another technique for getting quality outputs from chatbots, LLMs, is prompt engineering. And I'm sure you've seen some potential people making jokes about this being a future job, a prompt engineer. This might not happen, but at the very least, you can use these techniques to improve the quality of the outputs that you get from these LLMs. And as you can see on this slide here, there's a few different techniques you can use. I won't go through them all, but just very quickly go through chain of thought and automatic reasoning and tool use. So chain of thought prompts the language models to sequentially articulate and its reasoning for the steps that it's taken through problems. And it can improve the accuracy because it's kind of self-reflecting on what it's doing. Automatic reasoning and tool use essentially empowers the LLM to decide, okay, maybe I'm not very good at doing calculations, but I can use a function that can do a calculation. Moving on. So where is prompting very good? In what tasks does it succeed? So there's a graph here. See, there's various task types. We've got summarization, novel content. You can ask it to produce a story, for example. And going to the far right, you can see there's complex predictions and multi-class training that you can do. This is probably more suited for embedding models or for traditional machine learning models. So obviously prompting and LLMs, maybe not too useful there, but obviously you could use the art kind of functionality to improve that aspect if you needed to. I've highlighted on the top left where our project kind of makes use of a lot of these features of the LLM. And you can see, yeah, the key ones being on the diagonal. So the chat, the structured outputs, and the entity recognition. So entity data recognition, for example, being I want a bounding box around London. How does it then try and achieve that task? Because it first has to pick out London and then has to go pick out a bounding box around it.
Moving on to the components of the LLM. So talking about agents, they are just the evolution of print recipes like Clive already mentioned. They interact with the user and other agents as well. Their main role is to interpret the user query, access the relevant data sources, conduct the analysis, and then generate insightful output. However, these agents can be very useful for simple tasks, but they can also be complicated. Some of the challenges that we ran into was debugging and integration challenges. Also, keep in mind that these tools undergo frequent updates, making it difficult to maintain stable implementations. Here in this slide, we just showcase the different tools of LLMs, which is just a function that the LLM can use to produce output. So for examples 1 and 2, we can see that LLMs are very good at translating text and producing simple calculations, as well as accessing real-time information from the web, as showcased in example 3.
Perfect. And now on to the implementation of how we've done it. We've just discussed some knowledge. So our approach is to essentially make this interface very easy for the user and very user-friendly, and we want to hide the complexity where possible. So there's an architecture diagram here. Most of the work we've actually done is on the back end. So this is essentially stepping you through the process. We've got a user prompt. The person would like some data from those. How do we then pass that out? That's where the LLM comes in. We use the LLM. We translate that response into a JSON object. A JSON object allows us to pass it to a function external to the LLM. But before we do that, we have to validate. We have to check is it right? If it is, we can then proceed to the next step, and we can make that Mars request, that polytope request, and we can get some data. Or maybe the chatbot can then use other functions to visualize it. And then we can, on the far right, you see the front end. This is the bit the user interacts with, and this is our next step. Okay, so just some more details on the back end. So Nadia talked about the agent frameworks, and they can be quite complex. There's a lot of hype in the LLM world at the moment. We've kind of decided we'll use this where possible. We have a few demonstrations of two of these. But I think the issue right now is, because it's such an evolving field, whether this is how you interact with creating your own chatbot in the future is to be seen. In a year's time, will we have to do it this way? Or are things developing so fast, will the models get better that we actually do it a completely different way? Perfect. And then very quickly on JavaScript. So JavaScript is JavaScript object notation. It's essentially a hash map. If you have done computer science, you can have keys and you can have values. The keys have to be unique, and the values in our use case are the ones that we want the LLM to pass from the user's prompt and hopefully produce some useful output. And it's structured, ready for use in a downstream function. So this blog, if you look at this on the bottom, is very useful. And it shows all the ways you can try to get structured output from an LLM. I've highlighted the ones in yellow, the ones that we're using. So we're actually using a combination of all three of the main approaches. There are a lot of other approaches that you can see the dots kind of lead off to. But yeah, we essentially force the model, as far as possible, to format and return the JSON as best it can. We then have to validate it ourselves. We have to check, does it meet the specification we expected? And we also, it was very helpful, is to, in the prompt you provide to it, the LLM, you give it examples, and you also explicitly ask to give me JSON. Otherwise, it might not. And then coming on to the validation aspect, this title comes from a blog post as well, a very good one from the validator library. And you can see it's quite simple. We just essentially wrap the OpenAI call with one simple library, and it lets us use our pedantic models, which is essentially just a way you can force a data class in Python. There's lots of other ways you can do it too, but this is kind of the standard at the moment. And overall, good LLM validation is just good validation, as you would normally have in software projects.
Conversation flows is the ability for the AI to move the convo forward, such as asking for clarification on what's being asked. We don't need to worry about this when using ChatGPT Builder, but when using custom code, this will need to be included. Now moving on to the front end of things. ChatGPT Builder was used to create a custom AI. Unfortunately, you still need to host and expose API endpoints for custom tools, which can cause issues. Here we can see the custom AI that was made using ChatGPT Builder. We gave it instructions, all the documentations, prompts, descriptions, and at some point in this GIF, we will ask Holly to do something. So,
yep, so we can see that now, just on the right-hand side here. We're asking for a Mars request. And this was our version 0, and we got quite far with this. We might still implement this because essentially we have the functions, it's just we have to host them. So on the left-hand side, earlier on in the graph, you saw essentially you have to tell ChatGPT, go away and use this specification, these functions are these addresses, and it can use those external tools. Okay, moving forward, obviously that is somewhat restricted and it's reliant on OpenAI. So we wanted to also have an open alternative, and we found OpenWebUI, which is very useful. I think I'll just show the demo. So this doesn't show all the functionality, but it shows the main kind of chat interface. And also on the top left, you can see the different models you can select. So you can train different models, you can prompt models in different ways. You can use local models, you can use any API accessible model like OpenAI. And the benefit of this is you can actually keep all the data. You can be the admin of your hosted OpenWebUI, and you can kind of change the style. You can specify lots of various features to do with an LLM. You might want to make one more creative. You might want to make one less creative. And OpenWebUI lets you do that. Okay, coming on to the next steps. So our next steps, maybe I'll just focus on the left-hand side for now. This is our kind of, in a notebook, we have a question, and now the system is able to go away and get the response we need. We can then feed this into the Polytope library and get the data we need. So the next step is to refine the pedantic schema and also add a few other tools for the LM to use. Thank you very much for your time. Any questions, I'm happy to answer. And I thought I'd just leave you on this one last slide, which let us sink in for a second. So Sam Altman, the CEO of OpenAI, he's had this very insightful comment, which is there are two ways to build on AI at the moment, on LLMs. One approach is to assume that the world is static and the model won't get better. And if that's the case, we should do it the way kind of the world is working now, those LLM agents, the way they proposed. The other alternative is to hope, and I guess we'll see, that the models will get better, and a lot of this will be even easier in the future because the model will just take care of it. Thank you very much.
Thank you very much, Project Polly, for your presentation. Very impressive results so far. So I don't think we have questions for you now, but maybe at the end of the presentation, someone can raise and you can address the question. The next project team invited today is AI for weather forecasting models. The team members are Mihaela, Caian, Andrei, Gherasim, and Adrian Berlik. Mihaela and Andrei are here with us. They will be the presenters of their projects. Please, the floor is yours. I hand over to you now.
Thank you. Esperanza, can you see my screen?
Yes, we can see your screen.
Okay. So I will start our presentation. We have challenge 22, so XAI for weather forecasting models. These are our mentors. And the aim of the project is to identify those explainable features in AI models used in weather forecast that are able to be captured and explained by the AI models along with the training period. So physical features that are really reproduced, that are present in the atmosphere, like teleconnections or physical response at various time scales and space scales, that really are also captured by the AI models and can be explained, this feature. Why to do this? There are many reasons. Of course, the main one is to understand how the model works and if it can capture physical behavior in along the links it creates in the training period, it can help to improve further the prediction skill of the model, but also it can help to show us the limits of one or the other of the methods, the deterministic model and the AI model. I want to recall you that the models that we use here, AIFS and also Pangu, are already in parallel operational chains and provide weather forecast in parallel with the well-known and very highly skilled IFS model with similar skill or even better at times. So our approach here to try to understand and to extract explainability features from the AIFS model is to start physical-based approach for a given target process. Our target process here is the development and amplification or decay of mid-latitude cyclones, mid-latitude storms. Here you have a nice image here, and I will tell you how our approach is developed, the code and the package that we implemented, how can it be used further on, and the first results. Why the motivation of this study is here.
Sorry, Mihaela,
Yes.
to interrupt you, but we do not see the video. I don't know if you have activated it. It's if you want
sorry.
to. Yeah.
Sorry, I'm sorry.
It's
So
nicer.
have you seen this first page?
Yes, we have seen it. Perfect.
You have seen it. Okay. So the motivation of this study is, yes, it's obvious, I think, because as all we feel and we know, the storm frequency and amplitude is increased and already observed and even projected to become more frequent and with higher amplitude at regional scale, among these regions being Northern, Western, and Central Europe. So we are very, very interested on this. Here it is a plot from the European Environment Agency showing also the costs of this increasing frequency and intensity of storms. As you can see, the greenish colors are corresponding to storms and to floods, and you can see constant increase trend, and of course, unprecedented extremes in costs associated in the very last years. So there is full motivation in improving the approach and the model forecast, model prediction of these very, very challenging and important events. Here it is a slide showing our approach. So after selecting and extracting and proving, identifying the explainable features of the AI model, of course, we will then include it and link it to the skill of the model. As I said, sometimes, and not rare, the skill is better of the AIFS model, and also it has skill in representing extremes, but we want to know why and until when. So until when is a question that is approached by studying various ranges of prediction and limits in the error growth of the models. So after establishing the main, if there are, and if we can identify these explainable features, we will link it to the model skill, and the aim will be finally to help improve the forecast. For this link, we already extracted all the season. So our work already is done on the March, April, May, June 2024 storms. We selected 10 extreme storms on this interval and 120 days over the 4 months in which we perform simulations with various perturbation and various targets for explainability. Of course, these simulations will be layered then in 2 layers. One layer is a plus AI, so the layer when AI performs better than the deterministic model, and minus AI, where the deterministic model still captures well better the features. What we expect is, of course, having all the features that are slow flow drivers or long-term memory drivers as important addings, important input that help the better prediction in the AI case, because this model, the main advantage of this model is, of course, the fact that it has longer memory along the training period and uses this memory to reproduce the explainable features. So this is the point that we expect to justify and to enhance the prediction skill of the AIFS model. This is a list of the first selected features that we are testing. It is the for mid-latitude cyclone over Europe. It is the NAO phase, which is a slow driver. It is and the other teleconnection modes. I will have a slide and talk about this later. And then there is the jet, the maximal the wind at 300 hectopascal, with two main parameters, strength and meridional displacements. This is for the troposphere, and for the surface, of course, there are the sea ice anomalies and the SST. We focus on the Atlantic SST, as all you know. There are very hot anomaly in the Atlantic, mainly these last years, that are really driving this actual dramatic changes, let's say. For extremes approach, so this is for the overall approach method to extract the explainable features. For the extremes, however, we need to change, and here, because we all know that the main features driving the extremes are coupling the stratosphere and the troposphere. So we need to couple also here in our initial perturbations that we include in the model to be tested. So one link, it is the stratosphere plus troposphere link. It is a parameter that defines the strength of link. And among these is the jet collocation with the surface, because from the geostrophic theory and the ageostrophic circulation that is present when these are collocated, this turns to be strongly related to the amplification of extremes. So we will look in particular to the collocation of jet, upper level jet with surface low, but also to jet stability, jet streak location, this is a very important factor, and humidity affection and SST anomaly, of course. So mainly we already developed a package that is extracting and computing the perturbations on these main features, and including it as initial conditions in both in the AIFS model and in the PAGUS model. We have available this package. We have run the models with this package, and this, of course, will be at the end of the project made available in order to be tested for all other seasons and other years, not only for this season that we focused now. So this will be potentially extended. So here I put troposphere and the surface, but also the stratosphere will be. So what in the end we answer to these three main questions that hopefully will conduct improvements in the actual models. Is the AIFS model using teleconnections in prediction as the physical model, and if so, are these linked to improving forecast or not, and to which extent this is valid? Then for the extremes, the aspect of the extremes will be particularly approached, in which case and until which level of accuracy a IFS model can be useful for predicting mid-latitude cyclone extremes, and then the range of skill, until which time and for which situation AIFS can be a better solution or not. I will show here and describe just briefly the method that we implemented for two types of perturbation approaches that are the main slow drivers. One, it is the perturbation in the jet. Jet is the main driver, is like Yes, this is the main driver, or upper altitude main driver of storms. It is guiding, in fact, the storm tracks in Europe. And this is the main important element to be considered and to be analyzed. Is it explainable or not in the AIFS model as known from the physical knowledge and from representation of our best deterministic models. So here the algorithm of the perturbation was like this. We perturb the jet in two parameters, the strength and the stability, and perturb the zonal and the meridional velocities. For example, here, if you compare these two things, this is a perturbation that allows a stronger and unstable jet, and this is a perturbation that allows to parameterize a weaker and stable jet. And there are cross parameterizations. This, for example, using the two features with a stronger jet but more stable, and here with weaker jet but stronger stability. We performed simulations with AIFS model for all these perturbations along 10 days forecast, and here is one of the first results showing that we were very nicely pleased to see that indeed when using the simulation that performs the deeper, sorry, I have no time.
No, well,
the simulation that performs the highest deepening of the cyclone is the one with stronger jet and more unstable jet. That means more meridional shift and perturbation. So both U and V are amplified. And of course, just it was nice to see that it is not by hazard the results, because the plot that is filling in the storm track is the one where, in spite of the fact that the strength is increased, the meridionality variability is decreased. So this turns to be a very important feature to represent the correct and deepening at the timing of the storm event. This is for one of the extreme storm events. The second method that I really will.
Sorry, Mihaela. We encourage please to go in a hurry, because we still two remaining teams to take part.
Yes, I will go very quick.
50 minutes.
Yes.
Thank you. Sorry to interrupt you, but
no,
be
it's
aware,
okay.
Please be aware.
The second method, it is the perturbation in the phase. So this perturbation uses an empirical orthogonal function decomposition, and then the neighboring coefficients are used to compute the tendency of the phase. And this tendency is then used in simulations. Here we have simulation with a plus tendency towards a negative NAO phase and a tendency towards a positive NAO phase. And we see that indeed there is this phasing is one of the most important explainable features, because the tendency towards the negative phase is bringing the deepening of the cyclone tracks. So this is a good result, and it's showing that the AI model, without having physical equations, and it's able to extract this main feature as an explainable one. This is the same, but for other situations. I will not enter detail, but just to show that this is not unique case. So it appears as in a more systematic way for other storms in March, and here it is other features are territorial connection modes, but you see that these depend on the months. So for February we have AO and NAO, but for storm tracks in May and June, the remote connections show the Scandinavian mode, and the others mainly teleconnected. This is just to show that indeed our AOF perturbation algorithm is working. The difference is really nicely representing an NAO phase difference. And in the end, one slide showing that what is important is to take into account also the aspect of error growth in the AI methods that can be different to the error growth in the deterministic model, and then can limit the predictability range. Now I will give to Andrei for maybe 1 minute to explain.
Sorry, Mihaela. Sorry, but we have to remain in teams, and they all have right to present their projects.
So you will see yes, you will see all the plots here, because these are recorded.
Yes,
so
thank you very much.
about our pod and how we will further develop and what we have done until now. And our next steps are written here. Thank you very much, and I'm sorry if I
thank you very
much. Too much.
Thank you very much. So we quickly, there's no questions maybe at the end, but we are running out of time and all the projects need to have a say. So the next one is project CDSAPI request check. And we have Tom Calloway is also from Irina Sucoverschi, but Tom is presenting the project. Tom, the floor is yours, please.
Okay, just one moment, please. Hi, everyone. Irina Sucoverschi and I are the developer team for this Challenge 31, which has been broken into 2 teams, and we're team number 2. We'd like to thank the ECM WF mentors that have helped us a lot with answering questions and giving guidance, specifically Petrutz, Janita, and Angel. So a little bit of background on dataset access to the climate data store, otherwise known as CDS. It gives access to multiple datasets, and end users can fetch data for a dataset by composing a request in the form of Python code, specifically using a website tool available at the CDS Copernicus website, or they can compose it manually. And then they send the request to CDS using a Python library called CDSAPI. Oops. Okay. And so here's an example on the left of the web form on CDS. And you can see that there are dimensions like product type and variable, and they can select values for those dimensions. And then on the right, that eventually translates into a snippet of Python code that can be run using the CDS API client. And you'll queue your request in CDS, and eventually it will process that and give you a download. So each dataset has its own set of rules for what a valid request is. Specifically, there's a form schema and then a constraints rule set. The form schema gives all the options that you would see in the web form, details about the name of the dimension and the values that are acceptable, and some other things. The constraints actually show what the valid combinations of those options are. So it further constrains what you can actually select in the web and what will be accepted by CDS. So only one of these multiple constraint sets actually has to apply, but at least one has to apply in order for it to be a valid request. So what is the problem? Well, the user can send any request to CDS, but when its turn to be processed arrives, many manually composed requests are actually invalid and fail, but that is only discovered late in the process. Currently, only the web form applies both the form schema and the constraints to the user's request by activating or deactivating options while the user is filling out the form. But these constraints are not documented or used elsewhere, for instance, in the CDS API library that's used to make the request. So the main project deliverable for us is this repo, which is the CDS API extras Python library. And we expect this solution to help users detect, understand, and prevent request failures before they are even sent to the CDS servers. So this, by not clogging the system with too many failed requests, this will reduce the retrieval wait time for these users because they don't have to fix the problem and then send it again, which can be time consuming and confusing and frustrating. And then for the ECM WF systems and maintainers, this library could be incorporated into the CDS internal system to perform a preliminary validation and screen requests before they execute. And this, we expect, will reduce also the number of issues reported by users since they can fix them themselves, and thus the time spent by staff helping users. And without this new library, both users and staff will find it difficult to quickly analyze and find precise actionable fixes for the request failures. So we have 4 deliverables, and I'll give you an overview, well, some details about each one actually. So the first is just to detect if it's valid or invalid, if the request is invalid or invalid. And the main function that we provide is this validate request function call here at the bottom. And it takes the CDS API client the request, and then provides a validation summary of all the errors, if any, and also whether it was valid or not. We found in the process of testing the library against historical requests that there are many special cases inside the CDS system that you might not expect in terms of deviations from the form. So we support many of these deviations, specifically the dimension. Some dimensions are not specified in the schema. They might be documented elsewhere, but they definitely are valid according to the CDS system. The dimension might be required by the schema, but optional in practice in some or all cases. The dimension is not in the schema, but can be substituted for one or more schema-defined dimensions. And the values for these dimensions can sometimes have alternative values, involving type coercions, special patterns, or even specifying a range of values with a concise, flexible syntax. So some examples of special cases involve time and date. So you can specify the time using minutes or not as a string or as an integer. And date, you can specify ranges using various patterns. Also, you can specify a geographical area using north, south, east, west boundaries and 2 formats. And there are some type coercions at the top. So this is what a summary of request validation errors would look like for a request. You can see the area values are not within limits, or they have the wrong number of count, they're missing a boundary. And also, at least one of the constraints is not matching the request set. So the third deliverable is actually building a terminal-based request composer that will do the same thing that you saw in the web form, but doing this in the terminal. So if you're remoting into a system, that's possible, or if you just like working in the terminal, this is also possible. We're using the textualized library for this. It's still kind of at a prototype phase, and so we'll continue to work on this in the next few weeks, styling it a little better, but you can already see that it has the product type dimension. It shows it's required and lets them select the dimensions. Importantly, this will also make a call out to the remote service that CDS has to perform constraint validation, the same one that is actually used by the web form. So the same logic will be used there. And at the end, we'll also apply our own validation logic as a secondary validation. So finally, the fourth deliverable is checking for new data availability. The request composer will actually store requests into a local SQLite database and can also give the user the chance to send the request using the CDSAPI library. But before sending it, it will be able to check for availability of new data. So we have some remaining work to do. There's a new beta CDS system that is online, and the old system will go offline in September, early September, I believe. And we still need to perform the same QA that we've been doing with the old system with the new system, specifically because the CDSAPI syntax has changed for some keys or parameter names, and some values that were acceptable before are not necessarily valuable now. We need to do some more documentation of our library, and then also perform some requests with ADS and CEMS. So far, we've mostly done QA against CDS. So that's it for us. Thanks for your time.
Thank you very much, Tom, for the presentation. Very well done. And now we have the last. We don't have, I think, no, posted any questions. Just at the end, if something raised, you can address it. And the last team is about CDSAPI also. The same topic, and this project is formed by Andrei, Cotor, and Kaitlyn Talbu.
Esperanza, sorry,
yes.
Mario had a question, I think.
Okay.
He raised hand. Is that correct?
I couldn't see it.
Okay, Mario, if you have a question, please write it in the chat and we address it after the last presentation. Okay, sorry.
Okay, so the last team, optimizing CDSAPI, Andrei Cotor is with us today. So please, I hand over to you to introduce your project.
Hello, I'm sharing right now my screen. Yeah, so today I'll present to you some optimizations for the CDSAPI that me and my colleague Kaitlyn have been working on. So let's understand first why we need these optimizations. First, we would like to avoid requests with non-existing data. In order to understand this problem better, let's think of a dataset in a geometrical form, so as a hypercube in a multidimensional space. Of course, it would have empty spots. This is because there are certain combinations of parameters which either don't make sense or there isn't any recorded value for that. Now, as in the previous presentation you saw, there are some constraints for a dataset. You can think of this as subcubes, which show us what parts of the hypercube actually have values and shouldn't have empty spots. And of course, if an efficient request should avoid having empty spots or should be split in order to not have empty spots, because this is an extra burden on the system to process data, which is not there anyways. And the response for the initial request can be rebuilt locally. For instance, in the case of grep files, you can just concatenate the files in order to obtain one single. Also, the other problem that we target is avoiding expensive requests. These are very large requests, which are a burden on the system. Users that make such requests are getting penalized at this moment. And this situation can be solved using multiple smaller requests, which is better for the servers and also better for the users because they don't get any sort of penalization in this way. Now, this is an example of a constraint file. It's quite easy to read. It's in JSON format. So what it means is, for instance, if we look at the source, we have, in the case of soil, we have that data for versions latest 2.2 and 1.1 about nitrogen oxides. For instance, an example of an empty spot in the hypercube would be for the dimensions soil, latest and acetylene, or soil and version 3.0, because you can see that it doesn't match any sort of constraint. It means that there are no measurements in this case, or that it doesn't make any sense. Okay, now let's see the way that we tackle this problem. So first, we took the request and we intersected it with every constraint. In this way, we got a set of sub-requests, which we know for sure that they will not have empty spots because constraints don't have empty spots. But the problem is that the dimension of the set is quite large, and thus it can be even too large for CDSAPI and could create other kinds of problems, like flooding the server with requests. So the second step would be to reduce this number, and we noticed that some sub-requests can be merged without creating empty spots if they differ by only one variable. It's also very important, and it was very tricky, the fact that the order of the merges matter, because if we merge in a different order, we will get a different result set of sub-requests. So it's important to keep this in mind. Now, let's look at an example. So if the initial request asks for the aviation and soil sources for versions latest and 1.1 and the variable nitrogen oxides and acetylene, after splitting in sub-requests, you can see that we have 3 sub-requests. They are very similar to the constraints because they are formed after an intersection. And you can also see that this is not really the minimum number of sub-requests, as for the last 2 of them can be merged, as they only differ in version, and this doesn't create any empty spots. In the initial request, we would have an empty spot, for instance, for soil, latest, and acetylene. Now, the intersection was quite easy to do, but the most interesting topic in this part is the reunion strategies. So since the order of reunion matters, first of all, we thought about the backtracking, not the most obvious one with generating all the permutation, which is much too expensive for use in production, but one which generates connected components in a graph. It is good because it tries more options, but still being a backtracking, it's slower. The other approach that we took is an heuristic approach with maximal and minimal dimension reunion. So the idea is that we take every possible reunion, and at a step we select the reunion which gives us the minimal or the maximal size after this reunion. As a pro, it is very fast, but it doesn't guarantee the minimum number of sub-requests being an heuristic. So we did some experiments in order to figure out which of these approaches is the best. These experiments were done using real data registered from real users of the CDSAPI. And these are some highlights of our experiments. So you can see that the maximal dimension strategy works the best. It reduces the number of initial sub-requests quite a lot, and also it is not a large overhead, so the time is quite small. The backtracking, as expected, has a large time of running, and yeah, by not generating permutation, it's not always generating the minimum answer, and minimal dimension, it's quite bad. You can see it's not generating a value not even close to the minimum. Now, the second problem that we tackled is request optimization. So at this point, users need to follow guidelines in order to avoid creating very large requests. And our purpose was to automate this process and include it in the CDS API extras library. So we tackled this in a few different strategies. So we chose for splitting either the longest or shortest dimensions first, priority dimension, or random dimension, or a dimension with maximal cost reduction, which we figured out by making API calls to the costing endpoint, which already exists in the CDS API. Now let's look at an example of such a splitting. So this is an example of a request to the ERA 5. It's very expensive because it takes every month, every day, and every hour. And this request would exceed the maximum cost if you were to make it just like you see it here. So the idea is to split it into 4 different smaller requests, each of them having 6 hours. So we split by the hour dimension, by the time dimension, sorry. And in this way, we make sure that all the responses and the requests would fit into the size limit, so the user will not get penalized. And again, it's quite easy to merge the results in the front end and get in the client, so implicitly the front end, and get the actual initial request response. And this would be it.
Thank you very much, Andrei. Thank you very much for your presentation. Thanks. We have a comment from one of our mentors, Luke, and it's addressed to everyone. I can read it aloud. Luke says that he can help you order independent optimal hypercube margin if you like. Oh, okay. So
I guess that's for us. So
I think it's for everyone. So see, he has an algorithm for this. So if you are interested, please be in touch with Luke. Luke Jones is one of the mentors of one of our team. He's in WF mentor. So before handing Athena, we want to congratulate all the teams and thank you very much for sharing with your progress with us and for introducing them. So Athena,
yeah, thanks everyone. Sorry that we ran a little bit over. Closing the session, I would like to draw everyone's attention to the Code for Earth final day event, which will take place 18th of September. And it's a hybrid event. So stay tuned, register to our newsletter if you have not registered yet. Stay tuned, all the information will be available on our website. But you can already mark your calendars for the final day event, 18th of September, and you can participate remotely to this event. So I'm looking at Sarah. Anything else to mention? No. So we're good. Thanks again. A round of applause to all the speakers, to the participants, and have a fantastic day. For the participants, have a fantastic rest of the coding phase. And well, see you latest 18th of September. Thank you. Bye-bye.
Thank you. Bye.
Bye. Thank you.
Bye.